Alright guys, welcome to vodcast 8.1. We're going to talk about simple stoichiometry. I know that you're going to be massively thrilled and enthused because this is the stuff that I've been talking about since the beginning of the semester as being the really super important stuff. So let's get rolling. First off, what is stoichiometry? Stoichiometry is the study of quantitative relationships between reactants and products in a chemical reaction. And you're like, okay, that's great, Arnold. What does that really mean? So what that means is that if we have a balanced equation, okay, a balanced reaction, and we know one thing, so how many products or how many reactants or like this many grams of this thing or this many moles of this thing or this many atoms, then we can find how much of all of the other stuff we have. Okay, that's it in a nutshell. So what things do we need to know? We need to know how to complete and balance reactions, okay, and how to do mole conversions, okay? So just as a quick refresher, if you don't remember, Unit 7 had balancing reactions. Specifically, I believe that was 7.3, okay? And then Unit 3 is mole conversion. So if you need to go back and review that stuff, go check those out there. So just to review a little bit shortly on moles, and again, you can go back and watch the videos, but real quick, what is each thing? So a mole is Avogadro's number of anything. Avogadro's number is 6.022 times 10 to the 23rd. Usually for us in chemistry, it's going to mean that 1 mole of something equals 6.022 times 10 to the 23rd atoms or molecules or formula units. But it could be bananas, cars, warts on a frog, whatever. Okay? So where we're really going to use this the most in stoichiometry is with molar mass. So molar mass, remember, says how many grams are in 1 mole. So if we look up carbon on the periodic table, we would see that carbon has an atomic weight of 12.0 grams. That's where we get our molar mass reading. So 12.0 grams is equal to 1 mole of carbon. Remember that we can also do this for an individual formula. And the way that we would do that is I would say I've got 1 carbon times its molar mass of 12. Okay. And then I've got 4 hydrogens times its molar mass of 1. And that would give me 4.0. We'd add those up and I would get 16 grams per mole for carbon. Or I would get an equality like this that says 1 mole of methane, okay, CH4 equals 16.0 grams of that. Okay, so real quick, let's run through how to actually do the math on one. Remember that these are the problems where we've got a given, in this case, 43.2 grams of sodium. Real important that you write down what it is, not just the units, but what it is, because that's going to change here in stoichiometry. And we're looking for moles of sodium. So what am I looking for? Moles of Na. I look on the periodic table and I see that the molar mass of sodium is 23 grams of sodium equals 1 mole of sodium. Again, if it was a compound, I would have done a quick molar mass, okay, quick calculation. So I can go from grams to moles, which is what I want to do. So I'm going to set up my railroad tracks. I'm going to write my given in, 43.2 grams of sodium. I want to get rid of grams, so I'm going to put that on the bottom. Okay, and then 1 mole up top. Cancel what cancels. Grams of sodium. And I'm going to be left with moles of sodium. And when I punch it into my calculator, I get 1.88 moles of sodium. Okay, so it's just a quick refresher. Make sure that you knew how to do mole conversions. So what is stoichiometry all about? So all of the conversions that we used back in mole conversions, not shockingly, involved moles. Okay, now why that's important to us is because what we're going to do is we're going to take a balanced chemical equation, okay, like this one, propane plus oxygen, CO2 and water, obviously a combustion reaction. What we're going to do is we're going to take that and all of our coefficients, and remember if there is no coefficient, the coefficient is a 1, and those are going to be moles. And so what this problem would say then is that 1 mole of propane plus 5 moles of oxygen yields or produces 3 moles of CO2 and 4 moles of water. Okay? So all of that leads us to the idea of the mole ratio. This is like the key thing in stoichiometry, mole ratio. So what is a mole ratio then? A mole ratio is an equality between the coefficients on a balanced chemical equation. They're going to look like this. Okay? So I'm going to write out all of the possible mole ratios that I can get for this problem in equality form. So 1 mole of propane is equal to 5 moles of oxygen. How do I know that? There's an unspoken 1 there, right? Okay, and then 5 moles of oxygen right there. So that's where I get that. I can do that with all the other things too. 1 mole of propane is 3 moles of CO2. Okay, 3 moles of CO2. And 1 mole of propane is 4 moles of water. So it doesn't really matter what side of the equation stuff is on. What matters is what is the relationship to each other. And if we're talking about mole ratios, the coefficients are always in moles. So I can get all those. It doesn't have to be propane. I can do it with the oxygen as well. 5 moles of O2 is equal to 3 moles of CO2. Okay? 5 moles of O2 is also equal to 4 moles of water. Okay? And I could also say it could both be the two products as well. I don't have to have reactants in there every time I do this. So 3 moles of CO2 is equal to 4 moles of water. And those are the 6 mole ratios that I could get from this specific problem. Now the good news is you're not going to have to figure out and write out all this stuff for every equation. For every equation, you find the one that you need and you plug that one into the formula. Okay, so what do I mean by that? Well, here's a sample problem. This is the basic form of stoichiometry. We're going to work a few of these. These are not, it's not as difficult as it may seem as long as you understand where the mole ratios come from. So we're going to treat them like our old normal conversion factor problems. I've got a given, which in this case is 5.2 moles of propane. It is super important that you write down what it is. And if you weren't sure what was propane, you could have figured that out pretty simply. I know that's oxygen, that's carbon dioxide, that's water. Only one thing left. That has to be propane. Okay? So that's my given. My unknown is moles of water. Okay, so I'm looking for moles of H2O. And so the way that I always find that, the way that I can always turn one chemical into another chemical, so I want to turn C3H8 into water, is to take the mole ratio. So I've got 1 mole of propane and 4 moles of water. Okay? And why didn't I worry about oxygen or CO2? Because the only thing that the problem asked me is I had propane and water. Okay? So I relate those two things to each other. Their relationship is 1 to 4. All right? So now that I know that, I can go from moles of propane to moles of water. And so, like in typical conversion factor format, start with my given. It always goes in that first box. Make sure you label everything because everything's in moles. If I don't label it, I'm not knowing what moles I'm canceling out. So 1 mole of propane down at the bottom. 4 moles of H2O at the top. Okay. So bam, got that. And then you just punch it into the calculator. So we punch this into the calculator. We get 20.8 moles of water. Now, before I counted you off for units, in stoichiometry you also get counted off if you don't have what chemical it is. Got to have the chemical. The stoichiometric stuff doesn't make any sense without knowing what thing I've turned into what. Okay? So let's try another one. In this case, my given, again, is propane, but a different amount. So I've got 5.47 moles of propane, and again, propane is C3H8. You'll have propane like permanently emblazoned on your brain after this video. And then I'm looking for moles of CO2. So moles of CO2. So what's the relationship between them? So this time it's propane to CO2. And how many moles of propane do I have? 1. Remember, if nothing's there, you have 1. Okay? And this time it's going to be equal to 3 moles of CO2. Now, I know what you all are thinking, especially the guys. You're like, I don't even need to set up conversion factors. I can figure this stuff out without working it all out. So, given here. And I would tell you what, that is absolutely true for this part. But starting tomorrow, we'll start doing 3 or 4 steps conversion factors. So you really, in that case, have to know what's going on. You have to make sure you get everything canceled out right. So I want to cancel moles of propane, so I'm going to put 1 mole on the bottom. Now, I'm not just pulling 1 mole out of the air. That comes from right here. If that was 2 moles, I would have put 2 moles on the bottom. And then on the top, I put 3 moles of CO2. That's what I'm trying to get to. Cancel out what cancels, in this case moles, but not just moles, specifically moles of propane. So I know that my answer is going to be in moles of CO2, okay? And then we just punch it in the calculator. Punch it in the calculator, you're going to get something like 16.41. Got 3 sig figs here, 3 sig figs here. Yes, you have to do sig figs again, okay? All right, we're going to work one more, and then we'll have you guys try out some of these. So, how many moles of oxygen would be needed to burn 4.8 moles of propane? So again, my given is propane. Okay, I know you're like, why would you keep them the same every time? Just trying to build some consistency here so you know what you're doing. The unknown is moles of oxygen. How many moles of O2? Okay. What's my relationship now? 1 to 5. So that's my mole ratio. 1 mole of propane is equal to 5 moles of O2. Okay? And then we're going to set up our conversion factor, set up our railroad tracks. So put your given in, 4.8 moles of propane. Again, you guys have written propane enough. You probably have dreams about it. Or nightmares, I guess you would probably say. Okay, 1 mole of propane, again, that comes from here. 5 moles of oxygen. All right, cancel, cancel. Okay, and then we're going to just plug that into the calculator. Plug that into the calculator, I get 24 moles of O2. All right, so probably, I mean, most of you are probably going, that's pretty easy. A lot of you are probably saying, hey, I can do that in my head. I don't even need to set it up. And I understand that. That's somewhat plausible. Remember here that the key thing that we're looking for is the mole ratio. Anytime you find the relationship between any two things, that is a mole ratio. It can only be 2 at a time. Okay, even if you have like 20 things in your reaction, only 2 things at a time can work. But it's the mole ratio that is always the hardest stoichiometry. If you find yourself working on a stoichiometry problem and you haven't had moles in it anywhere, you're probably doing it wrong. Okay? So you should always stop and say, did I use a mole ratio? You're pretty much always going to use a mole ratio. All right? Thanks.